Oh, hello and welcome. SFU Math 152, Calculus 2. My name's Brenda. This is section 11.6, Absolute Convergence. So we're going to learn the difference between absolute convergence and conditional convergence. And we're going to learn how to use two more convergence tests, the ratio test and the root test. I like this quote. It's very, very true. You can always run at your best. And I think the key to, doing well at mathematics sometimes is to, when you go out and you run and it turns out to be not your best, that you don't let that influence what you do the next time you head out of the gates. You just kind of pick yourself up and get out there again. So, uh, you know, don't be too hard on yourself if at first something seems difficult. Okay, we're going to take a look at a problem that we might not yet be able to solve, and that would be how to see if this series here is convergent. There it is, n times 2 to the n divided by n factorial. Does that converge or not? And I mean, what we have seen a variety of different tests so far. First of all, it's not an alternating series, so we can't use that test. Secondly, yeah, we might be able to use a comparison test. That might work, but we certainly would find it difficult to use the integral test because of this factorial. We don't have a way of integrating the factorial function. For those of you who are interested in of that, you think to yourself, well, hey, that's interesting actually, that this is one of the things we've started to use fairly frequently, and we're going to see it's really important in the next little while, this factorial function. We know what the factorial function looks like. I mean, we can look at what it looks like on the integers here, 3, 4, like that, and then we can see, okay, there's 1 factorial at 1, and 2 factorial is 2, so that'd be 2. 3 factorial is 6, so that's somewhere up here at 6. And then 4 factorial is 24, so that's way actually off the top of the graph. So we could think, and in fact we also know that 0 factorial is 1. So we have some points, and we could actually ask ourselves, what curve would nicely go through all of those points? And then we can make a continuous version of the factorial function, which would allow us, say, for example, to assign meaning to 1.5 factorial. It would also, of course, if it was a nice enough function, allow us to integrate and differentiate. So I'm not the first person to say this, and this was an important question: how to assign such a function, and under what rules do you want? And you may want to take a look at this. This is not something that you need to know for Calculus 2, but it is of interest. So sometimes I just point to things of interest because personally I find mathematics extremely interesting, and you kind of want to be thinking like this all the time, actually, like, oh, here's something. I wonder if I did this, what would happen? Sometimes it's a small point and it's part of the course and you just cover it right then and there. Other times you manage to ask a question for which you need a lot more time and possibly a lot more skill to handle. But that's also interesting because you realize that you can ask difficult questions fairly easily. So for those of you that are just sort of interested, just maybe take a look, read up about the gamma function. Okay, we're not going to cover that in this course, just to reiterate, but just for interest. We're starting to see this factorial come up frequently. Okay, let's get some definitions down. Here we've got a series, and we call the series to be absolutely convergent if the absolute value of the terms converges. So if we make them all positive, then and it converges, and we call that absolutely convergent. So here's an example of an alternating series like that, and we write that also like that, and we call this series absolutely convergent because when I take the absolute value of this and get this, we already know that the sum of the reciprocals of the squares is convergent from earlier. So when all the terms are positive, it converges. So if I make half the terms negative, it also converges, and we call that absolutely convergent. Okay, we can also have a situation where a series is conditionally convergent, which means that if we take a series where some of the terms are positive and some are negative, and it converges, like we know this alternating series converges. However, if we take the absolute value, so I'm looking at this thing here, I take the absolute value, I get this thing here, and we know the harmonic series is divergent. So so the alternating harmonic series converges, but not the harmonic series. So that's different. So we call that conditionally convergent, and I would just write like this: the alternating harmonic series is conditionally convergent. Okay, so two words, absolute convergence and conditional convergence. If a series is absolutely convergent, then we can just simply, we say it's convergent. Okay, so here we're going to see how we could use this sort of little bit of subtlety here to talk about this series here. So we want to determine whether this series here is convergent or divergent. So I'm looking here at the numerator, and I know that sine can take on positive and negative values. So that is an observation. The series has both positive and negative terms. Okay, that's the first observation. Let's take a look at the first few terms. So in terms of the sign, I mean, this thing is always positive. So whether whether each term in the series is going to be positive or negative is determined only by the sign. So I take a look at the sign of 1, that's positive. It's a shorthand for positive. And I take a look at the sign of 2, that's also positive. Of course, we're working in radians. Sign of 3, positive. Sign of 4, negative. Okay. All right. So the fourth term is negative, and the first three are positive. So it's positive and negative terms, but it is not alternating. Okay. So it has both positive and negative terms, but sort of with a bit of investigation, we see it's not alternating. It doesn't go positive, negative, positive, negative, positive, negative. No, it goes positive, 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 negative, and then some other things. Okay. The main thing is doesn't matter what's happening further. We've determined from looking at the first 4 terms, it is not alternating. Not alternating. So we cannot use the alternating series test. Okay, so what we're going to do then is check if it's absolutely convergent first. Okay, check if absolutely convergent. Okay, and so basically I'm asking, does this function here, when I take the absolute value, does this thing converge? Okay, so how am I going to deal with that? Well, in this case, I'm going to observe that the absolute value of sine n is always less than or equal to 1 for all n. Okay, so that means that the sine of n divided by n squared plus 2n plus 1 is less than or equal to 1 over n squared plus 2n plus 1 for all n. Okay, now I'm going to take a look at this, and if this converges, then so will this, because I will have something smaller. And so if I have something that converges and it's bigger than something else, then that smaller thing converges. Okay, and we have, well, if I look at this thing here, I can say that 1 over n squared plus 2n plus 1 is less than 1 over n squared. I was going to go like this, for all n. That's shorthand. That means for all n. Okay, so, and we also then know, let's keep this chain of logic happening here, 1 over n squared is convergent. Why? B series Okay, therefore this thing converges by the comparison test. And that means that it's absolutely convergent. Therefore, if they don't happen to be all positive, we will, which they are not, this is convergent. Okay, by that above theorem, which stated what? Let me just reiterate what that theorem stated, that if a series is absolutely convergent, then it's convergent. Okay, so we're done. So we have now some amount of language and way of reasoning about series where some of the terms are positive and some of them are negative, but it's not alternating. Okay, now testing for absolute convergence. There's two main tests that we're going to use extensively, the ratio test and the root test. We're going to start with the ratio test. Okay, so this is going to be a test for absolute convergence. So here's the test here. This is how it works. You take ratio of the n plus first term over the nth term of the series. You take the limit as n goes to infinity and you get some number, L. If that number L is less than 1, the series is absolute convergent. If that number L is greater than 1, including if the limit is infinite, then the series is divergent. If you take that limit and you get 1, you're like, no info. Do not draw any conclusion. So you get an answer of 1. The ratio test is inconclusive. No evidence is being gleaned. You have merely taken one more limit in your life, and you've gotten better at taking limits. That's but you haven't gotten any information about your series. Okay, so we're going to do a few examples here, testing for convergence using the ratio test. So we see how this works. The ratio test is particularly nice, I find, when you see the factorials. You'll see why when we go through these examples. So let's take a look at A, this one here, A. So what we're going to do is form the limit of the n plus first term. So I'm going to take the n plus first term. That's going to look like this, n plus 1, 2 to the n plus 1 divided by n plus 1 factorial. That thing right there, let me just indicate what that is. I want to try to be as clear as possible. That thing I've just written here, let me even just box it here. That thing right there is a n plus 1. And then what I'm going to do is divide that by a n. So I divide by an, and an is n 2 to the n over n factorial. Okay, so now I've got a limit. If my limit taking skills hold up, I'll be able to tell whether this limit is less than 1, equal to 1, or greater than 1. That's all I care about. Just need to know that, and then I'll be able to possibly get some information about the convergence. So just to keep with the program here, this thing right here is an. Okay, let's see, right here. Okay. All right, so now let us take this limit. In almost all of these cases, what we're going to need to do is do a little bit of simplification and write out the factorial in a way that's more amenable to canceling. It's going to look like this. Limit as n goes to infinity. So what I'm going to do is I've got basically a ratio of two fractions. I'm going to take the reciprocal of the bottom fraction and multiply. So I'm going to have here n plus 1, 2 to the n plus 1 over n plus 1 factorial. And then I'm going to multiply by that reciprocal of the denominator, n factorial, n 2 to the n. Okay, now let's see, what can I do here? Okay, so here's the kind of thing you want to observe on these things. If I take n plus 1 and I multiply it by n factorial, what is that? I mean, n factorial is n times n minus 1 all the way down to 1. If I multiply by n plus 1, that is actually equal to this guy here. So those three things, uh, um, if I multiply those two in the numerator and then divide by that thing in the denominator, that is equal to 1. Assure yourself of that by writing out, I mean, try this, go write this. I mean, think of it this way perhaps. 6 times 5 factorial, this is what we basically have an example, it divided by 6 factorial. So that's an example where n is equal to 5. That's what I'm doing. Okay, we proceed here, and we've got 2 to the n plus 1 in the numerator and 2 to the n in the denominator. So I end up, when I do that division, with 2. And then I end up with, I'm not going to forget this guy, and still going to go to infinity. And then when I, what else do I have left? I have n left in the denominator. So then I can take this limit as n goes to infinity, I get 0. So the series under consideration, this guy right here, A, is absolutely convergent. Okay, this is less than 1. Okay, we'll do another one. We'll do B. Why not go in order? Okay, B. We are now going to, we're now looking at this one here, here. And what we're doing is exactly the same thing. We're going to take the limit as n goes to infinity of an plus 1. It's going to look like this. An plus 1 divided by an. Okay, the first thing is we're working with these absolute values, so I can immediately just get rid of anything with these -1 to the, these things can go right away. Those things are done. And now I have to just try to be clever about making sure that I simplify this thing so that I can see what this limit is. Let's go ahead and do that here. That's going to be the limit as n goes to infinity. I'm going to take the reciprocal and multiply just like I did in the previous case. So this will be 3n plus 1 over n plus 1 squared, and then I'm going to multiply that by n squared over 3n, like that. And what will that be equal to? Limit as n goes to infinity of 3n squared over n squared plus 2n plus 1, and that, folks, is 3. Okay, that is 3. That is greater than 1. B is divergent. Okay, let's just keep going here. We've got to do C and D. Let's check it out. C. Let's do C next. So that is the C here. Use some other symbol. What should I use? Let's think. Let's go like that. C. There. C. That is the alternating harmonic series. So I'm going to take the limit as n goes to infinity of the absolute value of -1 to the n plus 1 over n plus 1 divided by -1 to the n over n. So that's an plus 1 divided by an, and that's equal to the limit as n goes to infinity of n over n plus 1, and that's 1. No conclusion from the ratio test. No conclusion, okay? We don't know anything. We already know, in fact, that no conclusion. Well, let me just from the ratio test. Doesn't mean that we're completely toast, but it just means we tried the ratio test and we didn't get anywhere with that. So in fact, here we already saw we would use the alternating series test, and from that we would conclude. From that we concluded that it converges. So either maybe redo that, right? You can stop the video and redo that alternating series test. Remind yourself how to do that, and then come to the conclusion, the correct conclusion, that the alternating harmonic series converges. But you mustn't conclude that from the ratio test. Okay, and then just looking at the sort of other situation, which is D, which is the harmonic series itself. So let's take a look here at D. I'm running out of space here. I'm going to perform the ratio test on the harmonic series. So I'm going to take the limit as n goes to infinity. It's going to look exactly the same, of course, because the -1 goes away with the alternating. This thing just goes away. Other than that, it looks the same, but because of the absolute value signs, that's going away. So we know that this limit is 1. So I get no information again, no information from the ratio test. But this is the harmonic series. It's the harmonic series. We know by several methods, we know, and you will always remember this, we know this diverges. Okay, so we have a case up here where we got no information from the ratio test and the thing converged. Here we got no information from the ratio test and it diverged. In both cases, that no information was transmitted to us by the ratio test coming out to being a 1. So you must not draw any conclusion from the ratio test when it comes out to 1. Other than that, you can figure out whether something converges or diverges using this method, the ratio test. Particularly useful when you see factorials. And of the two tests I'm showing you today, the ratio test and the root test, they both have their place. If you just have to flat out guess which one should I try, I generally find the ratio test easier to use than the root test. But like all things in math, there are times when you need to really select the right thing. So you need to have both tools, but generally speaking, I like the ratio test better. Okay, here's the next of our two tests for today, and that is going to be the root test. And I'm just going to write to you when this one is useful. Convenient when nth powers appear. Okay, so that's when we want to be looking at using that. So we what we do is we take the limit as n goes to infinity of the nth power of the absolute value of the method that we're having for computing the terms. And we get a limit, and that limit might be less than 1. If that's the case, it's absolutely convergent. If it's greater than 1, it's divergent. And if it's equal to 1, note no conclusion. Okay, so we're not going to have we're not going to draw any information from either the root test or the ratio test when the limit is 1. We're going to go with the same game plan here. We are going to do 4 tests here using the root test, so you can see some examples of it in operation and how to draw the correct conclusion. So let's take a look at A first. I'm going to then take the limit. Okay, let me just write out what is an. An for A is this thing here, n to the n over 3 to the 1 plus 2n. That's what a to the n is. The root test tells me to take the limit as n goes to infinity of the nth root of the absolute value of a to the n. Okay, that's the root test. Okay, so I want to do that to when an is equal to this and see what happens. Okay, I'll just write it out. So what I'm doing here is I'm taking the limit as n goes to infinity of the nth root of this thing here, n to the n divided by 3 to the 1 plus 2n. And I think, oh no, this might be kind of a hard limit to see what's happening, and I'm going to have to try to somehow take that nth root. I'm going to need to, so what I'm thinking now is I need to algebraically simplify so I can hopefully get an nth power, which I take the nth root of and get rid of that nth root so I can manipulate this thing a little bit easier. So that's what I'm thinking. Along those line of thought, then I'm going to rewrite an. So I'm going to take a look at what's here underneath the nth root sign, and I'm going to think, okay, let me see if I can do a nicer job of this in some ways. I'm going to take n to the n over 3 to the 1 plus 2n, and I'm going to write that like this: n to the n of 3 times 3 to the 2n, and then I'm going to write that as, let's see, I've got 1/3, that's that 1 over 3, and then I'm going to write that as n over 3 squared all to the n. Okay, because that's n to the n over 3 to the 2n. And then I'm going to write that as, let's see, well, maybe I don't have to simplify that too much more, because I can take the nth root of that. Okay, let me stop there and then say, okay, then I'm going to now take this limit as n goes to infinity of the nth root of, and I'm going to put my algebraically modified form of this guy underneath that root sign. So it's going to be 1/3 n to the over 3 squared to the n. And I take that nth root and I get the limit as n goes to infinity, and I get 1 over the nth root of 3 times n over 3 squared, because the nth root of n over 3 squared to the n is n over 3 squared. Okay, so then I'm just going to take a careful look at this. The limit as n goes to infinity of this guy, I'm just wanting to know what's happening there. That looks like this. Limit n to infinity of 3 to the 1 over n. And then I can see that this exponent goes to 0, so this thing goes to 1. So this portion out in the front here is going to 1, and then I have multiplying that by n over 3 squared, and when n gets large, this thing gets large. Okay, so then I conclude that this series, this one here, n equals 1 to infinity of n to the n over 3 to the 1 plus 2n diverges. Okay, it's greater than 1. Okay, it diverges. And if I'm being nice, I'm cueing people to what I'm doing, and I was writing an exam in particular, I would say this diverges, and then I would say here by the root test. And just to make it absolutely clear what you were doing. Okay, that was A. Let us take a look at B. What is B? Another series B. It is the sum n equals 1 to infinity of this guy, 5n minus 3 minus n cubed over 7n cubed plus 2. And it goes to the n like that. And I'm wondering, does this series converge? So again, I'm going to use the root test, which means I'm going to take the limit as n goes to infinity of the nth root of the absolute value of an. So that in this case, for this series, is going to be the limit. So I'm going to take, it's going to be the limit as n goes to infinity of the absolute value of 5n minus 3n cubed over 7n cubed plus 2 to the n. I'm going to be taking the nth root. Okay, now pause. I see those absolute value signs, and I see that this thing may not be always positive. So I need to be careful about that. So now there's some caution with the absolute value. The terms are not always positive. Caution with absolute value. Okay, that means I'm going to check when, for example, we're taking n going from 1 to infinity, and I can see that when n is large, like n is 10 or something like that, that numerator is going to be negative. So at some point, and I can also see when n is 1, that numerator is positive. So at some point, the terms are, for some terms it's positive, and for some terms it is going to be negative. So I'm going to take a look at when does this guy equal 0? When does that equal to 0? So I factor out the n, and I see it equals 0 when n equals 0, and when n equals plus or minus, it's supposed to be a plus or minus the square root of 5/3. Okay, so that means when n is 1, it is negative. No, sorry. When n is 1, it's positive. And then by the time n is 2, it is already negative. So I need to be careful. So what I'm saying here is for n greater than 1, this guy is negative. Okay, so rather than worry about the 1 and the 2, we're taking a limit as, we're taking a limit as n goes to infinity, right? That's what we're interested in happening. And so why don't I just, instead of considering the sum from 1 to infinity, so this, just take a look at the sum of n equals 2 to infinity. If this thing converges, then adding in one more term won't change anything. So I'm just going to do this so that I can handle that negative positive issue more easily. So I'm just basically saying, look, if I can understand if this converges or diverges, then I add in the n equals 1 term. Don't care if it's positive or negative, it's finite, and that won't affect the convergence. Okay, so I'm just now going to realize that I've got something that is negative when I'm looking at this series here. When this thing here is negative for all n now. Once I've changed this to 2. A little bit of caution here. That's fine. Okay, so now what I'm going to do is I can remove the absolute value sign and turn the thing around. So I had that, I was here, right here, and now I'm going to remove the absolute value signs. The thing is negative, so I have to, I'm going to take the negative, and I'm going to get this here. I'm going to get 3n cubed minus 5n divided by 7n cubed plus 2. So I've reversed the order of the terms in the numerator, and that's going to be to the n, and then the whole thing is going to be to the 1 over n. So that allows this to cancel out, which is what you often want to see happening in the root test. And so then I've got here, this is the limit as n goes to infinity of 3n cubed minus 5n divided by 7n cubed plus 2, and that's the ratio of the leading coefficients. The limit is 3/7, and 3/7 is less than 1. Therefore, the original sequence, this guy here, is absolutely convergent by the root test. Okay, that is, we've seen one that diverged by the root test, one that is absolutely convergent by the root test, and our final example, we're going to take a look at one that, again, that we already know. Well, I guess it's our final two examples, the alternating harmonic series and the harmonic series, but they we're going to see the same kind of thing that we saw with the ratio test. So we have here the sum n equals, let's look at C first, the alternating series test, looking like this, minus 1 to the n over n. And so we're going to take this limit as n goes to infinity, n square root absolute value of an. I mean, clearly it was like if I saw this alternating series, like I would not immediately say, hey, I got a good idea, let's use the root test. No, I would not. I would look at that and go, it's an alternating series. Let's just use the alternating series test. That'll be fast and easy. But we're just going to show you here what happens when we decide to use the root test. It's a lot more work, and we don't get any information actually. So it's really not a good way to go. But so there's our root test. So in this case, that is going to be looking at the limit as what we're gonna do is look at the limit as n goes to infinity of the nth root of the absolute value of an. The absolute value of an is 1 over n, and then I'm going to look at the nth root. And then I see that this is an indeterminate form, 0 to the 0. That's the first thing that happens. So I'm like, okay, there is some limit, and that limit is this here. It's an indeterminate form, so I'm going to take the log on both sides, and that's going to be the limit as n goes to infinity of 1 over n times log 1 over n. And I see that as 0 times infinity. So then just a little bit more manipulation. The log of the limit is equal to the limit as n goes to infinity of log 1 over n divided by n. Then I've got it like this, infinity over infinity. And I can now, if this were continuous, I could use L'Hopital's rule. So I sometimes have rewritten these as the whole thing rewritten as x. Here's another way of doing it. Consider n to be a real number. Then that allows me to say this is continuous, and then I can simply use L'Hopital's rule. That's not what I wanted. This is going to be the limit as n goes to infinity. Yes, I do want that. I'm going to use L'Hopital's rule. I'm going to take the derivative of the numerator. That is going to be, what is the derivative of the numerator? The derivative of the log function is 1 over its argument times the derivative of the inside, minus 1 over n squared. And then I'm going to take the derivative of the denominator, and that's 1. And then I do some algebra, and let's see, that's going to be the limit as n goes to infinity, and that is n times minus 1 over n, so this becomes minus 1 over n, and that is 0. And that is log of the limit. Log of the limit is 0, so the limit is e to the 0, which is 1. No information. No information from the root test. And of course, because I've gone and taken this absolute value sign, I get no information from the root test for this one either, because when I take the absolute value, like this was D, right? But when I take the absolute value here in order to use the root test, these two things are basically the same once I take the absolute value. So I get no information for the alternating harmonic series from using the root test. I get no information for the harmonic series by using the root test. So I got no information. So in both of those cases, C and D, I get no information from the root test. I'm just going to make this really clear. C and D, no information from the root test. Okay, and just to reiterate, I know I've a little bit of a broken record on this, but let's for C, we already know that the alternating harmonic series converges. And in fact, the type of convergence is conditional. Converges. Okay, so the alternating harmonic series, this is, and we could use here the alternating series test. And we also know that the harmonic series diverges. Okay, and we saw a proof of that using partial sums, and we also saw a proof of that using the integral test. So maybe now would be a good time there was a way of doing it with partial sums, and there was a way of doing it with the integral test. It was a good idea right now. Why not? Now is the conclusion of this lecture. It might be a good time, right? Just to allow you to review some of the material from a couple of lectures ago, and if you and then just like solidify that, so you can go ahead, use the alternating series test to do this one, and then go ahead here and do both of these here. Do the partial sums and do the integral test, and assure yourself yet again that the harmonic series diverges. Okay, so this is now, we have now 2 more tools for looking at which series converge, and that in this lecture has been the ratio test and the root test. We've also here had an introduction to the idea of absolute and conditional convergence. And that is all for now. I will be back shortly. Thank you. Bye.